Molten rock, the building block of our planet, and water, the essential ingredient that makes all life possible, meet head-on in a spectacular confrontation on the Big Island of Hawaii. Recent, long-lived eruptions from Kilauea volcano, one of the most active in the world, have sent hot lava cascading into the ocean on 6 separate occasions. As the lava slowly adds new land to the island, the interaction of molten rock with the vast Pacific Ocean captures the imaginations of hundreds of viewers daily. Tentacles of lava appear to extend and retreat along virgin black sand beaches in a never-ending battle with the pounding surf. Standing near the towering steam clouds that mark the site of this interaction, one can easily see how the island of Hawaii is able to continually grow seaward. Only 1 million years ago, waves first washed ashore on the island that would be called Hawaii. From its base, 16,000 feet below on the ocean floor, it has now risen 13,000 feet above sea level to form the world's largest mountain. Hawaii's 2 most active volcanoes, Mauna Loa and Kilauea, continue to build new land through frequent eruptions. Many of these occurred not at the volcano summits, but on their flanks, along lines of structural weakness called rift zones. While some eruptions last only a few days, others continue for years, often sending lava all the way to the ocean. Eruptions along Kilauea's East Rift Zone, at Kapoho in 1960, and from Mauna Ulu between 1969 and 1972, created many acres of new land and presented scientists with the first modern opportunity to study Hawaiian land-building processes. Another Kilauea East Rift Zone eruption began in the early hours of January 3, 1983, on the remote eastern edge of Hawaii Volcanoes National Park. In the first weeks, the eruption produced a line of fountains called a curtain of fire, which gradually coalesced into a major vent. 47 episodes of spectacular fountaining over the next 3.5 years built an 800-foot-high cinder cone named Pu'u'o'o. On July 20, 1986, fissures opened up 2 miles east of Pu'u'o'o, and the eruption shifted to this new site. Soon lava began to pool over the vent, and in time a large, semicircular lava lake developed, which was named Kupayanaha. As magma passed beneath Pu'u'o'o, much of its dissolved gases and steam were released, ensuring that lava would rise gently into the lake without producing high fountains. Numerous short overflows from this lake built up a low mound called the lava shield. Longer-lived overflows formed channels that eventually roofed over to create lava tubes. The lava tubes insulated the flows, allowing them to travel farther without cooling and stagnating. The tube system gradually developed downslope, and within 4 months, lava had reached the sea. Successive flows established a stable tube system, which by mid-1987 extended the entire 7 miles from Kupayanaha to the ocean just east of Waha'ulaheo. When lava first reaches the ocean, it pours over old sea cliffs and flows across the beaches at numerous sites, only to be abruptly chilled and shattered by the surf. Much of this lava turns into Hawaii's famous black sand, which is found on all of the island's southern beaches. Broken fragments of hot lava, torn off by the waves, often float for several minutes, buoyed by steam escaping from their still molten interiors. Borne by ocean currents, gritty black sand and silt are deposited to form brand new beaches at sheltered locations along the coast. Prior to 1988, vertical sea cliffs faced the ocean here at Kamoamoa. Now thousands of cubic yards of sand have washed ashore to form the island's newest and largest black sand beach. As the coastal tube system becomes established, lava enters the water at fewer points, and the volume of lava at each point increases. This, in turn, increases the likelihood that a flow will persist through the surf zone, eventually building an underwater tube. The front of an underwater flow quickly chills, forming a rounded mass called pillow lava. As the flow moves forward, the pillows split open in a budding manner, producing successive pillows that push their way down the steep, rubbly slope. A network of submarine tubes, resembling the roots of a tree, help to stabilize this slope and allow it to act as a foundation for subsequent flows. In the relatively shallow water at the surface, lava spreads and advances seaward from the older sea cliffs to form a bench atop the rubble pile. In time, the bench grows until its height equals that of the former coastline, and it becomes incorporated into the landmass. Successive benches join to produce a fan of new land called a lava delta. This pair of deltas has taken over 2 years to form. Close to the original shore, where the water is shallow, only a small amount of rubble from the new flows is needed to support the active bench. As the new land builds further out into deeper water, more and more material must be deposited on the steep submarine slope. Though interlaced with pillow lavas, these huge rubble piles are permeated with water and are often so unstable that submarine tremors cause them to quiver. Small rock slides are common, and sudden major collapses of the active lava bench occur frequently enough to be a significant hazard to onlookers. Underwater, the collapsed bench will add to the debris pile upon which a new bench may soon form. process of new land formation is accompanied by a number of spectacular phenomena resulting from the often violent interaction of lava and water. The continuous close study of these events by scientists at the Hawaiian Volcano Observatory has led to significant discoveries about spatter formation, the growth of submarine tubes, and the development of littoral cones. When a submarine tube system is developing, underwater explosions commonly burst from the water's surface, sending up plumes of steam, cinder, and pieces of molten rock called spatter. Though seen most frequently close to the benches, occasional huge bursts have been observed originating in deep water, as far as 150 feet offshore. They are caused by steam explosions that occur after waves splash into the mouth of a tube. Instead of simply boiling off, the water is trapped in the tube by a surge of lava. The pressure of the flowing lava and the strength of the tube walls contain the pocket of steam until it either blows out the tube entrance or reaches a weak point. There, steam may escape as a single explosion or continue along like a string of firecrackers, blowing out every weak spot for some distance. A similar phenomenon occurs in tubes which are building through the surf zone. Small holes plugged by partially congealed lava act like pressure release valves. These serve as vents for steam and prevent the solidified sections of the tube wall from rupturing. On developing benches, powerful steam jets can fling highly fluid spatter hundreds of feet into the air. This particular episode began when water entered an inactive but still hot submarine tube buried deep in the rubble pile beneath the bench. The resulting high-velocity steam blew a 6-foot hole straight up through the overlying bench. Lava from ruptured surface tubes flowed into the hole only to be blown back out by the steam. Within minutes, a second opening appeared, and eventually a 20-foot diameter cavity developed in the bench. The largest explosions occur when benches collapse. Water instantly floods the broken submarine tubes, and the resulting steam blasts rocks and even boulders out over much of the surrounding landscape. Tubes, sliced off at the cliff face, pour huge amounts of lava straight out into the ocean, producing tremendous spatter bursts and enormous clouds of cinder and ash. An entire bench, often more than 200 yards long and 50 yards wide, may disappear in less than a minute. Cinder, ash, and spatter, collectively called tephra, can be blown in all directions during explosive events. Large amounts fall in the water as well as on land. Most spatter is ejected as small chunks or twisted, ropey-looking pieces of glowing lava. Major explosions, however, can occur without warning and hurl out much larger globs. Pieces weighing several pounds are not uncommon, and chunks the size of suitcases have been observed. Most of the tephra is made up of fine particles of cinder and ash. These are light enough to be blown some distance from the eruption, where they may cover a large area of the ground to the depth of several inches or more. Close to the ocean, where most of the material falls, piles of tephra as much as 20 feet high may form. These are called littoral cones and are only found near the sites of intense explosive activity. The seaward side of these cones is loose, steep, and prone to wave erosion. Unless the cone becomes surrounded by a stable lava delta, it may cave in or wash away soon after it is deposited. The channeled lava flows that feed littoral cones are often broad, swift, and very fluid. Some appear to burst right out of the sea cliff and rush almost straight into the water. Others enter the sea more gently, and in places, water can actually become incorporated into the lava stream. When this happens, the water flashes into steam, causing a bubble to form in the lava. Sometimes these are just little blobs the size of a grapefruit or smaller. Other times, however, more water is present and larger bubbles form. In less than a second, these can grow from small bulges on the flow to incandescent domes a foot or more in diameter. As the expanding steam pushes outward, the top of the lava bubble begins to tear apart into glowing net-like strands. Less than 2 seconds after the bubble begins to form, it disintegrates in a steam-propelled explosion that hurls spatter skyward. The same process occurs during submarine explosions, often blowing out chunks of the tube wall. These large spatter bursts were produced from bubbles 8 to 12 feet in diameter. In extremely fast-moving lava flows, standing waves may form when the flow hits an obstruction and curls back upon itself. Surf, breaking on the flow, dumps water into the curl, where it can mix with the lava. Instead of exploding like conventional spatter, the flow produces a stream of lava bubbles. Similarly, when lava flows over boulders, eddies may develop. Water gets trapped in these pockets and expands as a steady burst of steam, which blows out through the lava in a hosing motion. Huge spatter bubbles result. Most of these bubbles are 8 to 12 feet in diameter, though some larger than a 2-car garage have been observed. This phenomenon happens only rarely and is usually shrouded in heavy steam. Few people have ever witnessed its occurrence. The bubbles form thin membranes of volcanic glass that shatter the instant they solidify. Wafted up with the rising steam clouds, the pieces can be carried for hundreds of yards downwind to be deposited as a carpet of fine fragments called limu o pele, or seaweed of the Hawaiian fire goddess, by local Hawaiian residents. When first seen in February 1988, it was identified by volcanologists to be a new scientific phenomenon. The steam clouds that carry aloft the limu opele and the finer particles of tephra also contain large quantities of seawater, which fall back as an intermittent drizzle of extremely acidic rain. Weak funnel clouds occasionally descend from the plume and can be seen harmlessly swirling along underneath. The new land over which they pass is black and desolate. Sulfurous fumes seep from glowing cracks that traverse the coastline, and a palpable feeling of primordial activity hangs in the air. The waves and the land seem to play a tug of war. These processes of growth and erosion, which combine to form and shape this new land, have continued unabated since the first islands in the Hawaiian chain rose from the sea millions of years ago. They will undoubtedly work together long into the future on islands that have yet to form. The submarine volcano, Loihi, growing from the ocean floor about 15 miles south of Hawaii, will one day emerge from the sea to continue the legacy of Hawaiian land building, which started on islands that have long since vanished beneath the waves.